Hi, welcome to this video for performance engineering for ML engineers. This is going to be the first part of the series, and in this lecture, we're going to be going over this outline. So first, we will be looking at performance engineering fundamentals and the hardware-software interface. We will then be looking at how to identify if a kernel is compute or memory bound. We will then predict the performance bottlenecks using a concept known as arithmetic intensity. We will then explain why NumPy is 10 to 100x faster than naive Python. Then we will understand the memory wall and why cache locality matters. And then finally, we will appreciate the value of optimized libraries like BLAS. So if you are an ML engineer and you want to get a deeper insight into building production ML systems, then this video would hopefully be useful to you. And in terms of the prerequisites, there are no prerequisites as such. If you have a basic understanding of Python and some basic understanding of ML systems, then this should be a good video for you. Thanks, and let's go ahead. Okay, so for the purpose of this video, we will be taking a look and diving deeper into the matrix multiplication kernel. And one of the reasons to do that is that matrix multiplication is the most foundational operation in machine learning and deep learning. And it is also a really fertile ground for examining a lot of the optimizations that we can make from a systems perspective. So yeah, let's take a look at matrix multiplication and see what are the obvious and naive ways of implementing matrix multiplication and how these can be further optimized. So before we get into any of the code, this would just be a refresher on the basics of matrix multiplication. So let's assume that we have two matrices, A and B. A is of size m by n and B is of size n by k. Then the matrix multiplication of A and B would be this matrix C, which has a size of m by k. And the way that we actually do matrix multiplication is that we are taking the dot product of the rows of A and the columns of B. So for any element in C I comma j, C of I comma j is simply the dot product of the ith row of A and the jth column of B. So yeah, this and you can examine the output matrix C and verify that this indeed does work. So yeah, now that we have the basics of matrix multiplication, this is just like a brief refresher. We will now go ahead and see how to actually implement this in Python. Okay, so before we go further, I just realized that the way that we have named the axes of the matrices is slightly different from the convention and the practices that people typically follow when talking about matrix multiplication. So I'm just going to do a minor renaming. Nothing about the matrix multiplication actually changes. We will just be renaming the shapes and the axes of the matrices just to be more in line with the conventions that are typically followed. So instead of A being a matrix of size m by n, let's just assume that A is a matrix of size m by k. And similarly, we can assume then that B is a matrix of size k by n. And this would give us a resultant output matrix C of size m by n. Okay, so now that we have this minor renaming out of the way, let's go ahead and just go over the high-level pseudocode for the matrix multiplication. Awesome. So now I'm just going to lay out the high-level pseudocode. So we first want to iterate through the rows of A. So for I in range, and A has m rows. So for I in range m, we will then iterate through the columns of B. So for j in range, and B has n columns, so for j in range n, and then we will iterate through this column axis k between A and B. So for lowercase k in range uppercase k, we will actually compute the dot product here. So C of I comma j, we will accumulate this as just a simple scalar multiplication of A of I comma k times B of k comma j. So we're just indexing A and B, and we are computing the dot product of the ith row of A and the kth column of and the jth column of B to give C of I comma j. So yeah, this is the high level pseudocode. There are 3 nested loops. Now that we have laid this pseudocode, let's go into the Python code for matrix multiplication. Okay, so now let's go ahead and implement the matrix multiplication in code. And a link to this Colab notebook is included in the description of the video. So in this notebook, I basically have the first cell where I have set up the inputs, and in the next cell we just have a basic test case to verify the correctness of our matrix multiplication that we will implement in the next cell. So here I have laid out the basic scaffolding for the naive matrix multiplication implementation. So this function takes as input 2 matrices A and B, and we want to compute the matrix multiplication of A and B. So we just verify that we can actually do the matrix multiplication by checking the correct shapes. And here the condition is that the number of columns in A should match the number of rows in B. And then we initialize C to be all zeros of size m by n, and let us now implement the triple nested loop that we saw in the pseudocode. So we first iterate through the rows of A. So for I in range m, then we iterate through the columns of B. So for j in range n, and then we iterate through this common axis uppercase A. So for lowercase k in range of uppercase A, and here we are basically just doing the dot product of the ith row of A and the jth column of B. So we iterate through k, and we accumulate the scalar multiplication of the kth element of the ith row of A and the kth element of the jth column of B. So C of I comma j is simply the accumulation of the scalar multiplication of A of I comma k and B of k comma j. Okay, so now let's just verify that this is correct. So I'm going to run this test case, and fine. All of the conditions pass. So yeah, we can confirm that we have implemented an extremely naive matrix multiplication using 3 nested for loops. And as you might realize, that this is an extremely inefficient way of implementing matrix multiplication. And so let's go ahead and optimize this step by step. Okay, so before we go ahead and optimize this knife matrix multiplication, I think this would be a good time to pause and just benchmark this initial implementation that we have, so that we can compare and contrast the optimizations that we will be making to this initial extremely naive implementation that we have. So I have already set up some benchmarking code. You can take a look at this in the link shared in the description. And the way that we will be doing the benchmarking is that we have three examples in this case, and we will compute the runtime that it takes for us to finish execution of these three examples. And for each example, we will be computing the matrix multiplication 5 times. So we have this configuration num underscore runs, which basically tells us how many times we will simulate the matrix multiplication. And then once we have iterated 5 times, we will count the minimum runtime as our benchmark for that example. So I'm just going to go ahead and run this test case, and this will take about a minute to run. So I'm going to pause the recording, and we'll see what output we get. Okay, so now that the code has finished executing, let's just go ahead and see the results. So we had 3 examples, and we have the runtime. We have the minimum runtime over 5 runs for each example. So for the first example, it takes approximately 0.17 seconds to run. For the second, it takes about 1.4 seconds, and the third example takes about 12.3 seconds to run because we're dealing with large matrices. So what I'm going to do is I'm just going to copy this, and I'm just going to keep a track of this in the last cell, and then as we go ahead and make optimizations, we will come back and visit and see if the optimizations actually make any change to these runtimes. So yeah, let's go ahead. Okay, so we will now go ahead and make our very first optimization to this matrix multiplication routine. Okay, so I think one of the lowest hanging fruits in this current implementation is the observation that we are actually writing to C of I comma j k times inside this loop, and this is probably not ideal. So what we can do instead is that we can just maintain an accumulator which accumulates the dot product over here, and then once we have finished this loop over k, we can just set C of I comma j to this accumulator. And the reason why we want to do this is that accumulating the results in a variable and writing to the variable takes much less time than actually going ahead and manipulating the C matrix in memory. So we can make use of this fact by adding an accumulator. Let's just call this variable s, and we initialize this to 0. I'll just make a comment, accumulator to reduce repeated writes to C. And instead of writing to C of I comma j, we can just write to this accumulator that we initialize to 0. So at the end of this iteration over k, the accumulator s contains the dot product of the ith row and the jth column of B. And then we can set C of I comma j just once to this accumulator that has accumulated the dot product. Okay, so this is a quite simple change, but let's just check if this is indeed correct. Okay, so the test cases pass, and now we will actually benchmark the runtimes to see if it actually makes any change in the runtimes. So I'll just wait for this to finish execution, and then we can go ahead and examine the results. Okay, so this is finished running. I'll just go ahead and see what we get. Okay, so all results now contains the updated runtimes for this small optimization that we made for accumulating the dot product in an accumulator and then writing to memory just once. So as we can see, we have noticed some improvements already. We can see that for the first example, the runtime has dropped from 0.17 to 0.11. And for the second example, it's dropped from 1.37 to 0.89. And then for the third example, it's dropped from 12.3 to 7.2. So as we can see, this very small change has actually made a decent improvement already. So this let's also just keep a track of this. So naive accumulator, and this is what we see for this very first optimization. Okay, so let's move on to the next. All right, so before we go deeper into the optimizations on the matrix multiply, I think that this is a good time to talk a little more deeply about matrix multiplication from a systems perspective. And more concretely, we will be looking at some of the practical artifacts of the matrix multiply, specifically the number of flops in a matrix multiply, and also the amount of memory that is moved in the matrix multiply. So you can think of the number of flops as a somewhat analogous and a practical flavor to the notion of time complexity. So we can analyze the number of flops in a matrix multiply by just taking a look at the pseudocode. And as you can see in the pseudocode, we basically have this triple for loop. So we know that that the time complexity of the matrix multiply is about cubic in nature, and within this innermost for loop, we can see that we are basically performing two floating point operations, and the first one is this multiply of these two elements of A and B. And after we do this multiplication, we just do a simple accumulation and add that to C of I comma j, which in the optimization that we just saw, we accumulate in the local accumulator S. So just to summarize, inside this inner for loop, we basically have two floating point operations, one multiplication and one addition. And hence, we can represent the number of flops in a matrix multiply in terms of the outermost for loop is of size does m iterations, and then this second for loop iterates n times. The innermost for loop iterates k times, and inside this innermost for loop, we are doing two floating point operations, which then gives us this constant factor 2. And hence, an approximate number of floating point operations in the matrix multiply is roughly 2m and k. And this number is going to pop up a few times. So it's a good idea to really understand where this 2m and k comes from. And yeah, so I hope this is clear, and we will now move on to computing the number or the amount of memory moved in the matrix multiply operation. Okay, so now that we have analyzed the number of flops in the matrix multiply, it now makes sense to analyze the memory traffic of matrix multiply, which is just um, basically the amount of memory that we move around in this operation. And this is a practical variant for the space complexity. And the way that we compute the number of or the amount of memory that we move around is basically to take a look at the amount of memory reads and the amount of memory writes. So first, we will estimate the number of memory reads, and if we come back and take a look at our matrix multiplication pseudocode, we see that we are basically performing two memory reads, which is we read from A and we read from B inside this inner K loop. So we perform two memory reads inside this, and since this is nested inside M, N, and K, we are basically doing two reads M and K times, and hence the amount of memory reads that we perform in the matrix multiply is just two M N K. Now, if we take a look at the number of memory writes, we can again come back to our pseudocode, and we see that we are performing one memory write, which is to C. We do this once inside the innermost loop. So basically, we do MNK writes. However, we saw that we can actually do a little bit better, and we don't need to write inside this innermost loop. What we can do is that we can have this accumulator S, and we can accumulate the dot product in S, and then we can just write once outside the scale loop. So we can then just write the C after we're done with accumulating the dot product. So we don't need to do MNK writes, but instead, since this single write operation is placed outside the innermost loop, we actually do this write operation mn times. So hence we can estimate the number of writes in our matrix multiply as m times n, and hence the total number of memory operations that we perform in our matrix multiply is simply just the number of reads plus the number of writes. So that's 2mnk plus mn. And now, when we want to estimate the total amount of memory that we move around, we basically multiply the number of memory operations by the element size. We can just call this LM size. And this basically just represents the data type of the matrices. So basically, if we're dealing with integer matrices, which are 4 bytes, then this would then the element size would be 4 bytes. If you're dealing with 64-bit floating point operations, then this would be 8 bytes. So yeah, I hope you got the point. element size basically just represents the size or the data type of our matrices, and 2 mnk plus mn times the data type or the size of memory will give us the total amount of memory that we move around in the matrix multiply. So I hope this is clear, and let's move on. Okay, so now let's just briefly talk about a very important concept in computer science. And this concept is that modern computers today have two fundamental limits. The first limit is compute throughput. So compute throughput is defined as how many flops per second can the CPU or GPU do. So for example, modern CPUs in 2025 can do roughly 1 teraflop per second. So that's 10 to the 12 flops per second. And modern GPUs today can do roughly 100 teraflop per second. So this is the limit in terms of the compute throughput that a processor can do today. Now, the second limit that that modern processors encounter is the memory bandwidth, or how many bytes per second can the CPU move from RAM. And modern CPUs in 2025 roughly have a memory bandwidth of 50 to 100 GB per second. And on the other hand, modern GPUs can move roughly 1000 GB per second. So these are the two fundamental limits that that we will grapple with and that we will explore further as we really try to understand to find the bottleneck in our code. All right, now I also want to talk about one of the most important concepts in performance engineering, and that is the arithmetic intensity. So the arithmetic intensity measures how much computational work you can do per byte of data moved. And this is measured as flops per bytes moved. And the intuition behind the arithmetic intensity is basically to think of it as a measure of compute density, or how many calculations you can squeeze out of each byte that you fetch from memory. And the arithmetic intensity is used to analyze whether a kernel or a piece of code is bound by memory or by compute, and we will see how to do that shortly. Okay, so next, let's understand what it means to have low arithmetic intensity and high arithmetic intensity. So, taking a look at this expression, if we have low arithmetic intensity, it means that we are doing less computation per bytes moved. So we're doing fewer flops for every byte that we move, and hence programs or pieces of code that have low arithmetic intensity are usually memory bound. And on the other hand, if a kernel has high arithmetic intensity, it means that it is doing more work or more flops per every byte that it moves, and hence it is compute bound. Also, one note before we move further: one way to increase or improve the arithmetic intensity of a program or kernel is to reuse more of the memory that you fetch. What this in turn does is that it increases the amount of computation that we do per byte of memory that we move from memory, and hence reusing memory more leads to an improvement in the flops per bytes, and hence an increase in the arithmetic intensity. So that is one of the most simplest and the natural ways to increase or improve the arithmetic intensity of a piece of code. Okay, so now let us take a look at the roofline plot, which is a really interesting concept, and it is a convenient way to visualize whether a kernel is compute bound or memory bound. So what it means to be compute bound is that the code is limited by the processor's computation speed. And what it means to be memory bound is that the code is limited by the memory bandwidth of the system. So as you might have identified, both of these are system dependent, the processor's computation speed and the memory bandwidth. And basically, what we have control over as a programmer is the arithmetic intensity of our code. So based on the arithmetic intensity, we will either lie in the memory bound region or the compute bound region. So let's take a look at that now. So basically, the roofline plot can be drawn or plotted as follows. The x-axis is the arithmetic intensity. So it is basically the axis that we as a programmer or a system designer have control over. And the y-axis represents the peak flops, and this is hardware dependent. Now, as you might have noticed already, this plot has two distinct regions. One is this sloping line, which actually represents the memory bounded region. And the other is this flat line, which represents the compute bounded region. And now the main decision rule of the roofline method is basically a comparison between the arithmetic intensity times the memory bandwidth and the peak flops of the hardware. So basically, if the arithmetic intensity times the bandwidth is less than the peak flops, then our kernel is memory bound, or it lies in this region. And if the arithmetic intensity times the memory bandwidth is greater than or equal to the peak flops, then our kernel is compute bound. So this represents this region. And basically, again, we will just contextualize this decision rule in terms of the plot, just to make things more clear. And then we will also go through a small example. So let's take a step back and really look at the roofline model just from a much more simpler perspective. So, so we have the arithmetic intensity, which is the flops per bytes moved. And this is basically, like an indication of how performant our code is. And we multiply this by the memory bandwidth of the system, which is a physical constraint that is imposed by the system on our code. So what this means, again, is, okay, if I'm doing so many flops per byte that I move from memory, and if I am allowed to only move these many bytes from memory, then basically how much work am I doing? So this so basically the arithmetic intensity times the memory bandwidth is, if we just take a look at the units, so this is flops per bytes times bytes, this essentially gives us some amount of achievable flops for our system. And now we know that the system imposes another condition on us. Actually, before that, let us again just represent this in terms of a simple plot. So here the x-axis is the arithmetic intensity, and the y-axis is flops. So it's just a unit of like the amount of work, and basically this is represented by this linear plot, and whose slope is the memory bandwidth. So this is a slope, and we multiply the slope by the x-axis to get this linear plot. Now, this is all well and done, but this plot extends indefinitely, right? So as your arithmetic intensity, uh, in the limit as the arithmetic intensity goes to infinity, the number of flops also goes to infinity. But we know that this is not possible within the constraints of our computer. The computer cannot do infinite flops per second. So there's a hardware specific constraint, and that is actually represented by this horizontal line for peak flops. So this is the maximum amount of computation that you can do on the hardware. So basically, then our plot is sort of it basically behaves linearly with respect to arithmetic intensity up to a particular point, and then it just flattens out. Okay, so now let's take a look at a concrete example. So let's assume that we're working on a system that has memory bandwidth of 200 GB per second, and let's assume that it has a throughput. So throughput is basically just the flops per second, and all of our computations, just to make it simple, we will be assuming flops per second. So throughput or peak flops per second is let's just say five teraflops. So on our hardware, we can do a maximum of 5 teraflops per second. So now the plot would look something like so. So we will basically okay. So arithmetic intensity, flops, and again, you could either consider the y-axis as flops or flops per second, but let's just assume that since we are considering like a per second scale anyways, let's just keep it simple and call the y-axis flops. So so 5 teraflops or 5,000 gigaflops is basically this line, and now we have this linear plot which goes like so, and whose slope, which is represented by m, is 200 GB per second. So now let's assume we're given, or let's assume that our kernel has an arithmetic intensity of 10 flops per byte. And we need to determine whether our kernel is memory or compute bound. So the way that we would do that, again, using this decision rule that we took a look at, we will be using the arithmetic intensity times the memory bandwidth, and we will compare that to our peak flops, and then see which one is higher. So in our example, the arithmetic intensity 10 times the memory bandwidth, 200 GB per second, gives us 2000 teraflops. No, sorry, 2000 gigaflops, which is equal to 2 teraflops. And our peak flops given by the throughput is peak flops is 5000 gigaflops or 5 teraflops. And we know that the arithmetic intensity times the memory bandwidth, which is 2000, is less than 5000, and hence our kernel must be memory bound. So our kernel with the arithmetic intensity of 10 lies in the memory bound region of the roofline plot. Okay, so now that we know that our kernel is memory bound, let's take a look at what our arithmetic intensity would have to be for our kernel to be considered compute bound. So the way we would do that is by finding uh, this point at which basically the slope meets this horizontal line. So the way that we would do that is, let's assume that the arithmetic intensity at which this happens, let's just call it x. So x times 200 should be equal to 5000, and this gives us 5000 divided by 200, so 25. So basically uh, for any arithmetic intensity greater than 25, we would the kernel would be considered compute bound. And now let's just quickly do a recap of what it means to be memory bound versus compute bound. So for memory bound kernels, they actually starve the CPU. So the CPU is ready to calculate, but it has to sit idle, waiting for the data to arrive from memory. And this corresponds to the slanting line of the plot. And the fix in this case is to improve the kernel by reusing more of the data, which actually leads to a higher value of arithmetic intensity, or to improve the memory bandwidth, either like by a faster RAM or a higher memory bandwidth capacity. And note here that actually improving the performance or the throughput of the CPU actually has no impact on the performance of the kernel for the memory bound case. And then when we take a look at the compute bound scenario, this often results in overwhelming the CPU. So the data is piling up because the CPU cannot process the instructions fast enough. And of course, this corresponds to the flat region of the plot. And the fix in this case is to vectorize the code or to use more cores or some sort of parallelism. Okay, so now finally let's come back to the code and take a look at some of the concepts in action. And these are concepts that we have already spoken about before, so this should just be a quick refresher. Let's also once refresh our latest implementation of the naive matrix multiplication. So basically here we have this triple for loop where we iterate over the rows of A, columns of B, and then we iterate over K and compute the dot product of the rows of A and the columns of B. In our very first implementation, we actually were writing to C of I comma J k times inside this loop, and we realized that that was not efficient. Um, and instead of writing k times, what we could do is we could just maintain an accumulator variable s, which accumulates the dot product inside this loop k, and finally sets the dot product just once to see outside outside this k loop. And so that's just a quick refresher on the state of our matrix multiplication code. And over here in this cell, I've just defined two functions which give us the flops and the memory bytes consumed in the matrix multiplication thus far. And the flops are 2 MNK. We saw this in our discussion a while back, and the memory bytes consumed or moved is simply the amount of memory reads and the amount of memory writes, and the reads are given by 2 MNK and the writes by MN, and the total memory touched is just um, the reads plus writes times the element size of each cell um, in our matrix multiplication. And the default value is 32 bytes, uh, which corresponds to the data type of float 32. Okay, so similar format to what we had over here in the time benchmarking code. We just set up a similar loop over here, and we are just computing the flops, the memory bytes, and we compute the arithmetic intensity. So let's just run this code. Okay, so as we can see here, we get the same value for arithmetic intensity for all sizes of our matrix multiplication because, of course, the arithmetic intensity does not depend on the size of the matrix multiplication, but just our implementation of matrix multiplication, and the ratio of the memory bytes. The ratio of the flops over bytes consumed is the same regardless of the size of the matrices that we are doing the matrix multiplication over. And we see that the arithmetic intensity is 0.25 for our current implementation of matrix multiplication. And also, I've added just a little bit of code here, which serves as a good guide for us. And basically, on modern CPUs, any arithmetic intensity value of less than 1 is likely memory bound, and AI values greater than 10 are considered compute bound, and between 1 and 10 are balanced arithmetic intensity values. So as we can see, the arithmetic intensity value of 0.25 is less than 1, and this indicates to us that our matrix multiplication kernel currently is memory bound, which means that the CPU is waiting for a longer time to just get the data from memory. And there are a lot of improvements that we can make to the algorithm in terms of data reuse and in terms of the efficiency of the computation per bytes that we move from memory. So I think that's a good hint regarding what we're going to be doing next. So let's move on.
Okay, awesome. So now let's take a look at some ways and strategies by which we can make better use of each piece of data that we fetch from memory. And in order to do that, it is really important to understand this concept called spatial locality, and to really understand how the CPU utilizes its cache memory. So something that we've discussed a little bit in this video and also in a previous video on PyTorch internals is this concept of the row major layout. So in Python and C++, and specifically in this case NumPy, data is stored in a row major order. So what that means is that all the elements in a particular row are stored consecutively in memory. So let's say we have a 4 by 4 matrix. In that case, all of the elements in the first row are first stored consecutively, and then all of the elements in the second row. And the way that CPUs fetch this data and store it in the CPU cache is typically these uh, in these sequences called cache lines. And cache lines typically involve 64 bytes, so that's 16 32-bit floating point numbers. And whenever you access a particular element of a NumPy matrix, that element, as well as the local elements with respect to that element, are fetched by the CPU and stored in cache. So basically, I'm just reiterating what I just mentioned. So whenever you access an element b of k comma j, the CPU loads that element plus the nearby elements into its cache. And so first, let's understand why the current loop order that we use for our matrix multiplication is actually not very efficient when it comes to the CPU utilizing the memory that it fetches to its cache. So you might now be extremely familiar with this triple for loop. So you iterate over the rows of the first matrix, the columns of the second matrix, and then the innermost loop. You're iterating over this common dimension of the columns of the first matrix and the rows of the second matrix, which is k. So as you will notice, all of the elements of A. So let's first take a look at the data access of the first matrix A. So in our inner for loop, we access elements of A in row major order. So we're looping over K, and K is this second dimension. And as we increase K, we access the next element of a particular row I in A. So basically, the access of the first matrix A is actually in row major order. So that is good when it comes to cache, because whenever we access A of I comma k, we also fetch the neighboring elements with respect to A of I comma A. A of I comma k. And then as we increment this k loop, we actually don't need to refetch elements of A into the CPU's cache, because these elements that we access in consecutive iterations have actually already been loaded into the cache of the CPU. So with regards to the matrix A, we're fine. It is optimal with respect to cache. But now let's take a look at the access of the memory of matrix B. So what happens is that when in this inner loop K, we're actually accessing the elements of B not in the row major order, but we're actually going in, we're walking down the columns of C. We're not walking down the rows of B. So the B access pattern looks something like this. So let's say you have some fixed J. In this inner loop, we are accessing B of 0 comma j, and then B of 1 comma j, and then B of 2 comma j. So we're essentially walking down a column. And the problem over here is that column elements are k elements apart in memory. So for really large values of k, you have typically large strides. And strides, again, is a concept that we discussed in the PyTorch internals video. But basically what it means is that every consecutive element of B that we access is actually located far away in memory. Which, and like typically in memory, we store these elements in row major order, but all of our accesses are basically walking down the columns of B. And as a result, each consecutive B access will lead to a cache miss if B is a really large matrix, and each cache miss actually forces the CPU to fetch a cache line from memory, which is actually not very efficient, and this is a big cause of the latency, and this is what makes the current implementation of the matrix multiplication actually not very cache efficient. So yeah, just to summarize, in our current implementation of matrix multiplication, it is this fetch from B that is actually inefficient with respect to cache. So let's now take a look at how we can actually fix this. Okay, so we're now going to make our matrix multiplication code cache friendly. And the primary principle that we're going to employ in order to do this is to ensure that every consecutive element of the matrices A and B that we access should be located consecutively in memory with a stride of 1. Um, so uh, if you remember, the issue that we were facing in our current that so the issue that we face in our current version of the matrix multiplication is that for accesses of matrix B, these accesses are basically column wise. So every consecutive element of matrix B that we access is actually down a column, and hence these consecutive accesses of matrix B are not located consecutively in memory. And we know that the CPU fetches data in cache lines, so it fetches consecutively laid out elements in memory and loads it onto cache. And since we were accessing the matrix B by walking down the columns of B, we were essentially running into cache misses, which was making our algorithm not very efficient with respect to cache. So in order to prevent this from happening, we're just going to simply ensure that all of the consecutive accesses for both matrices A and B have a stride of 1. So what we're going to do basically is change the ordering of our loops from the IJK order to IKJ. And let's take a look at first let's actually take a look at what that entails and the side effects of changing this order from IJK to IKJ. And then let me convince you that this is actually correct and this will give us a valid matrix multiplication algorithm. So first, let's just see what happens when we change the order. So the first for loop iteration is the same. So for I in range m, and then we change this the next nested for loop uh, to iterate over k. And what this means is that we will now in a temporary variable a store a of I comma k. And then finally, in our innermost loop, we iterate over j, or we iterate over n. Um, and basically, what this gives us is that that now all of our consecutive accesses of B are located at a stride of 1. So in this inner for loop, we are we are like, let's say we fix k to be 1, for example, then when we iterate over j, we are essentially basically walking down the rows of b, and hence we are going in the row major order. And similarly for A, we basically ensure that within this innermost for loop, A is unchanged, and then in our secondmost for loop, again we iterate over K, which is the second dimension, and all the consecutive accesses of A are again just in row major order. So for both A and B, and also the writes to C, all of these three operations are actually in row major order with respect to the matrices. Okay, now let's take a look at why this is actually correct. How come we can just change the ordering of the loops in our matrix multiplication to give us a valid solution to the matrix multiplication? And I'm not going to go into a lot of detail here, and I will sort of leave this as an exercise to the viewer. But I'm going to just basically lay out the core principle of how we can sort of in a back of the hand way get an idea for why changing the loop order will actually give us a valid solution to the matrix multiplication. And that is because we simply just need to ensure in our matrix multiplication triple loops that we iterate over each combination of I, j, and k exactly once. We don't do any less and not any more. So each combination of I, j, k, we just iterate once. And we know that by simply changing the order of the loops, we're not changing like how many combinations of ijk that we iterate over. And then once we change the order, this just changes how our algorithm behaves with respect to cache and the memory accesses. And here we saw that we had to make just a minor tweak to the algorithm where we keep a constant in during the course of this innermost loop. But apart from that, uh, nothing changes in the actual floating point operations that we do in our matrix multiplication. So this is the core idea. I would highly encourage you to take a notebook and walk through an example and see why this actually works in practice. But for the purposes of this video, I am going to leave this as an exercise to the viewer. So yeah, let's move on now. Okay, so now let's take a look at how we can implement this cache optimized loop order changed version of the matrix multiplication that we just spoke about. So I have the basic framework of the function set up here. And now I'm going to implement the triple loop where we actually compute the matrix multiplication. So I'm just going to set up the matrix C, which is going to be the output. So this is going to be a size, this is going to be a matrix of size m by n. And we can set the data type to be the same data type as one of the matrices that we pass as input. Okay. So now we implement the workhorse of our algorithm. So we first iterate over the rows of A. So for I in range M. And then here in our in the cache optimized version of the matrix multiplication, we want to go in the ikj order. So we iterate now over k. So for k in range k.
And then we need to store the value of a. So I comma k, the value of matrix A that we will be considering is a of I comma k, and this will actually be constant in the innermost for loop that we will be iterating over. So we will store a of I comma k in a temporary variable called a. And then finally we have the innermost loop. So for j in range n, and then here we actually will be setting c of I comma j. And note here that we cannot actually store this in a temporary variable and then finally store this into matrix C, because we actually will be computing and accumulating the matrix multiplication over each combination of I comma j inside this loop. So we can't have a temporary variable that we then finally assign to C, because this changes for each iteration. So we will be directly writing to the matrix C of I comma j, and we will be accumulating the dot product of A of I comma k times B of k comma j. And again, you can go through and trace out the dot products and see that what we are doing is we're just instead of doing the entire dot product for a particular element of C, we are distributing the dot product by just accumulating um, the multiplication of A and B. And so yeah, this is the algorithm, and then we finally return C. Okay, so now that we have implemented the cache optimized matrix multiplication by changing the loop order from ijk to ikj, let's now benchmark this implementation and see if it gives us any performance improvements. So what I'm going to do is we have this benchmarking code, and I'm just going to comment out the previous matrix multiplication call that we were calling, and then I'm just going to replace this with the call to the cache optimized version of matrix multiplication that we just implemented. And now that we have this, I am just going to run the benchmarking code on these three test cases that we have. Okay, so now that the test cases have finished running, let's see if we actually get any performance improvement or not. Okay, so these are the runtimes of the cache optimized matrix multiplication, and now let's just compare it with what we saw before. Okay, so cache optimized ikj, and I think we have an interesting situation where, as you can see, the cache optimized version of matrix multiplication has actually given us a worse performance than our best implementation of the naive matrix multiplication using the accumulator. So we see that for the first test case, we are approximately 0.01 seconds slower, and then for the second test case, we're about 0.1 second slower, and for the last test case, we are actually slower by approximately 2 seconds. And there is a really subtle reason why this is the case, and we will talk about it now.
Okay, now to some of you, it might seem that the cache optimized version is slower because we are actually doing more writes to C in the cache optimized version than in our naive IJK version of the matrix multiplication. And this is primarily because in the IJK version of the matrix multiplication, we had the local accumulator S, which was basically computing a running uh, computing like the dot product in a running manner and then finally writing it to the C array only once. But for the IKJ version or the cache optimized version of the matrix multiplication, we basically have we write to the matrix C inside the innermost for loop. And it might seem from outside that these repeated writes could actually be the reason why the cache optimized version is slower. But I'm just going to dispel that myth by looking at some of the details of what is actually happening. So I'm going to scroll down. Okay, yeah. So the reason why writes don't matter as much is that uh, if we take a look at these writes, we are accessing the elements of C in strides of one. So basically, what happens is that all of C's elements in the row stay inside the cache. So the writes to C of I comma j are sequential, which means that instead of writing to memory, we are actually all of these elements they likely stay in the L1 cache of the processor, and like we directly write to the cache and not the memory. Um, and another subtle reason is that the write buffers also absorb repeated writes. So like modern CPUs do not do multiple write operations sequentially, but they have basically write buffers, and repeated writes to the same cache line are basically nearly free. And another point is that the penalty that we pay for cache misses is drastically more than L1 cache writes. So we can see that that a cache miss leads to approximately 100 to 300 cycles of the CPU fetching from main memory, whereas L1 cache write just accounts for 1 to 4 CPU cycles. So even with the extra k writes, even with the extra writes inside the innermost for loop, the the penalty that we pay for cache misses is drastically more, and hence the bottleneck is actually not the cache. The bottleneck is not the repeated writes to C, but it is something even more subtle. So the real reason that our cache optimized version of the matrix multiplication is slower is because of something known as the Python overhead. So Python is an interpreted language, and it is quirky in a lot of ways and not as smart as compiled languages, which benefit from the performance optimizations that these compiled languages get because of the compiler. So, in order to understand this more concretely, um, I think it's important to keep in mind that whenever we write to C of I comma j in pure Python, this actually involves a NumPy NumPy array indexing overhead, and since NumPy arrays are in C, we also read from C and then do the addition or the accumulation, and then we write back
to these C arrays. So in pure Python, NumPy array indexing is actually expensive. Um, and the reason that this would actually be much faster in C and C++ is again what I mentioned, that in compiled code, the compiler recognizes that C of I comma j is reused across the innermost loop, and hence it keeps it in a CPU register or an L1 cache. And then the repeated read, modify, writes become essentially free. And we get the cache benefits for accessing uh, all of the matrices A, B, and C in sequential memory. So, so the lesson from this example is that language really matters for optimization, and cache-aware algorithms assume compiled code where the compiler can optimize away redundant memory accesses. And in Python, the interpreter it executes each statement or write to C literally, and C of I comma j is a separate array access every time, and it doesn't optimize away by the compiler. So I hope this is clear. And now we will take a look at how we can actually leverage compilation in Python.
So now you might be thinking how we can compile our Python code. And in order to do this, we're going to make use of a library called Numba, which is a very popular numerical programming library in Python. So we're going to import this thing called NJIT, which stands for Number Just in Time. We will first just implement and see how to do this in code, and then I will go into a little bit of detail about what actually happens under the hood. But this is going to be extremely simple. What we will do is that in order to convert, let's just start with the naive matrix multiplication. If we want to, if we want to, if we want to write this as, or if we want to transform the execution of this function into compiled code, what we will do is we'll just copy the function, and I'll just call this naive matmul number, and I'm just going to use the NJIT decorator above this function like so. And this is it. This is as simple as it can get. Okay, so now that we've seen how to convert a function in Python to its compiled version, very simply by just using by first importing NJIT from Numba, and then just using the NJIT decorator above the function declaration. Let's just go ahead and see how and just see this in action. So what I'm going to do is I'm just going to see if this function works fine. I'm just gonna copy some of this code, and okay, and what I'm gonna do is naive matmul number, and yeah. Okay, so yeah, this works fine. Okay, so now you might have noticed that the first time, or the first test case that we ran took a while for it to finish executing. So like we just had this first print statement, and then it took some time until it printed the second, and then once it printed the second, like it ran all of the test cases immediately. So and like you can just verify this by just by going behind a few seconds, and then and just reviewing the section where we ran the test cases, and you will notice this slight delay or lag after we printed this first test case, and it took some time to actually do the matrix multiplication. And that is because in Numba, when we call this function for the first time, it actually compiles the Python code uh, to to a compiled version via LLVM, which then converts it to assembly, and all consequent function calls to the naive Matmul number are actually um, calling the executable. So basically, the key point here is that the very first time that we call this function, it takes extra time for us to finish the execution, because we first need to compile and then run the compiled version of the code. So typically what happens is that in any piece of code that we write in Numba, before we actually call the function in production, we can just have some sort of a setup function that runs. It's called the warm up, which basically just involves us calling the NJIT function with a very small like input, just for the purposes of compiling the Python function, and then all of the subsequent calls to the function that we just compiled leverage the compiled code, so we don't need to worry. But the very first time, we actually have this extra compilation step, which we can actually do before it is called in production. So typically, what happens is that, okay, so let's see this in action. So what we're going to do is we're just going to have a warm up step, warm up NJIT, and the first call compiles. So we're just going to define this above these test cases that we run below. And what we're going to do is I'm just going to run this function on onto matrices. They don't need to be very relevant. We can just have two matrices containing zeros of size 1, 1, and we don't really care about the output either. So we can just run this, and okay, and then once we have and now once we have warmed up naive Matmul number, we can again just see that all of these test cases run instantly, and that is because we already have the compiled version of the code that we leverage, and this compilation happened in the warm-up step. So when we actually run the test cases, we can just make use of this nice compiled version. And it's important to make sure that in this first warm-up call, we pass in relatively small inputs to ensure that most of the time that it takes to run this is spent in compilation. And then once the compilation is done, we don't want to spend too much time calling the function on the input, so we can just pass in two relatively small matrices, and then the subsequent calls to this function leverage this nice compiled version that we already have. So yeah. Okay, so now that we have the we have the number version of the naive matrix multiplication, we can do the same for the cache optimized version of the matrix multiplication as well. So what I'm going to do is I'm just going to copy this code. It's exactly the same. And we can copy it here, and I'm just going to add the number suffix. Again, I'm just going to change the name of the function so that they're two separate. And I'll just add the NJIT decorator. It's as simple as that. And then what I'm going to do is I'm just going to add the warm-up step. So warm-up NJIT for cache optimized. And I'm going to do this now. So yeah, so now that we have the compiled version of this function, I am simply just going to run it in this loop again, just to see that that it's working fine. So just copy this and paste it here, and then let's run this. And as you can see, all of the test cases were executed instantly, and this wouldn't have been the case if we had not done the warm-up for this function above. Okay, so now let's just spend a little bit of time to understand how the Numba compilation pipeline works. So basically, the first step, we have the Python source code, and then Numba analyzes and type infers this code, and then it makes use of LLVM under the hood, which then compiles and optimizes the code and converts it to the native machine code or assembly of the hardware that you're running it on. So this is basically what the compilation pipeline looks like. And again, just to reiterate, in Numba, it is really critical to separate the compilation and the execution of the code that we are compiling. So the first Numba call includes some compilation time, which is typically like a few seconds. So we warm up on tiny inputs first, and then we benchmark on the real inputs and use it in production. And this is done to separate the compilation time from the execution time. So yeah, I think that's it for Numba and how we can leverage it in Python. We're now going to take a look at actually benchmarking this code, and let's take a look if this leads to any performance improvements. Okay, so now that we have the Numba versions of our naive matrix multiplication and the cache optimized matrix multiplication, let's go ahead and benchmark these implementations to see what performance gains we get. So what I'm going to do is I'm going to come back to our benchmarking code. I'm going to comment out the old function call, and I'm going to now test with our newly implemented Numba versions. So first, I'm going to test using the naive matrix multiplication in Numba. Let's go ahead and see what we get. Okay, wow, that ran almost instantaneously. So we can clearly see that that there is a big improvement in the efficiency and the runtime, and we can see that for our earlier implementations, the last test case took about 7 to 9 seconds to run, and I know here it runs almost instantaneously. So we can see that so just implementing the matrix multiplication in Numba itself gives us a huge performance boost. So I'm just gonna go and keep a note of the runtimes that we observed. So for Numba, naive, Matmul, this is what we see. Okay, so now let's test with the cache optimized version of the Numba matrix multiplication.
Cool. So now let's go back to our benchmarking code. I'm gonna comment this out and now test on the cache optimized number version of the matrix multiplication. Let's see what we get. Again, it runs almost instantaneously. And wow, this is an even greater performance boost. So let's just observe the values. So number cache optimized Matmul. Let's see what it looks like. So yeah, we can see that that okay. Let's just take a look at like the number naive matrix multiplication and the number cache optimized matrix multiplication. We can see that for the last test case, the cache optimized matrix multiplication is actually roughly 10 times more efficient in the cache optimized version as opposed to the naive version. So the last test case ran at roughly 0.3 seconds for the number naive matrix multiplication, and then for the number cache optimized matrix multiplication, the last test case ran in 0.002 seconds. So that's a 10x improvement in in performance for the large matrices. So yeah, I think we should be really happy now that we can actually see the performance benefits of using the cache optimized version of the matrix multiplication when we actually make use of compiled code. So this is really good news. And now let's just do a more thorough benchmarking exercise. This is going to be the last piece of code that we go over, and this will be sort of a summary of all of the results that we have seen so far, and we will also compare these versions of the matrix multiplication that we implemented from scratch with the NumPy versions of the matrix multiplication to see how much gap there is. So let's go ahead and do that. Okay, my bad. Before we go to the final part of this video, I also just want to see what the NumPy implementation of the matrix multiplication gives us in terms of performance. So I'm just gonna uh, comment this line out, and let's just see what what the native NumPy version of the matrix multiplication gives us. So I'm just going to the add operator is the NumPy operator for matrix multiplication. Just going to go ahead and run this. Again, runs extremely quickly, and let's see what we get. Okay, so we can see that again, this is a further improvement. We can see that the last test case runs in 0.0005 seconds, which is roughly 3 times faster than what we got in our number cache optimized version of the matrix multiplication. So NumPy Matmul, and this is what we see. But this just means that our code is that NumPy is 3 times more efficient, roughly, um, compared to our version of matrix multiplication that we implemented from scratch. So we can see that this last test case is 0.0005, and our implementation is 0.002. So this is not bad by any means, but of course, this also tells us that we have still some room for improvement. Um, so yeah, I hope the summary of all of the runtimes is instructive, and now let's just visualize this in terms of a plot and sort of like summarize all of our experiments so far.
Okay, so now I have added some code here, which basically does something extremely similar to what we did above here, where we benchmark each version of our matrix multiplication, but it does this in a much more concise manner inside this function called benchmark Matmul, and it also computes the performance over these three matrix sizes, and then um, we actually plot the performance in the form of this plot over here. So yeah, we have this plot performance function, and finally we have this beautiful plot which summarizes the performance, which in this case is measured in terms of throughput or the gigaflops per second, and we can see this plot. So here we have three samples or data points corresponding to the three sizes of the test cases of the matrices. And this plot is extremely instructive because this shows us that our Numba version of the cache optimized matrix multiplication comes pretty close to the optimized NumPy version of the matrix multiplication, which is a gold standard and the reference point. And we can see that our Numba version of the naive matrix multiplication gives us a decent improvement over the pure Python versions down below. But of course, we can see that the cache optimizations that we made gave us a further improvement, and we could only see that when we removed the Python overhead and we switched to compiled code. And down below, we see that that the pure Python versions of the matrix multiplication are roughly equivalent, and in fact, the cache optimized Python version of the code is actually so like this orange line is below the blue line, so it's a little bit worse off as compared to the pure Python naive version of the matrix multiplication, and that's because the interpreter adds overhead, which basically nullifies the cache optimizations that we made. So in order to truly see the benefit of the cache optimized version of the matrix multiplication, we saw that we had to switch to compile. We had to switch to compiled code, and that is where we truly saw the benefits of the cache optimization. So basically, once we remove the Python overhead or the Python interpreter overhead, the memory access patterns actually matter, and that is when we see the performance benefits of our cache optimized version of the matrix multiplication. So I hope this video was instructive. I think a lot of the code patterns that we saw here are extremely useful and important when doing performance engineering of our code. So I think we covered a lot in this video. This is going to be it for this video, but I intend to make 2 more videos, and in the next version of this video, we're going to be looking at tiled matrix multiplication and see how that further improves the performance of our matrix multiplication kernel, and then we will see if we are able to get even further to the gold standard NumPy version of the matrix multiplication. And I also plan to cover profiling and other techniques that are extremely crucial in performance engineering in the video after that. So I hope this was instructive, and thanks a lot for sticking by, and cheers. See you in the next video. Also, finally, you can find the links to the code and the notes that we used in this video in the description of this YouTube video. So yeah, thanks.